We're going to discuss parameterized curves. Today we'll look at the difference between the notion of a path, the notion of a curve, and the notion of the trajectory of a path. We'll also introduce ourselves to velocity vectors, and we'll start doing some differentiation again. And we'll also see how we can talk about the intuitive notion of the tangent line of a path or of a curve. For a reference, you can find this material in section 3.1 of the course textbook. Okay, so the main objects that we're interested in today are paths. So a path in Rn is a continuous function whose domain is some interval of real numbers, and the codomain is some big Rn. So we'll also say that a path is going to be a vector-valued function. So the values that the path takes, the outputs, are going to be vectors. And here, when we say that a path is continuous, what we mean is that each of these component functions, which are now scalar, real-valued component functions, each of these functions is continuous. So for example, we can consider the following function. This is going to give us a path in R2. So it takes in real numbers and it spits out a vector inside of R2. So here we see that we have the component functions x of t and y of t, and we have obviously x of t is 3 minus 3t and y of t is 2t. And this path describes a line. So we can see this by thinking about the inputs, the input interval, which is the real interval, the interval of all real numbers. What the path does is it takes any real number and it maps it into R2, and you should really think of this as taking this infinite long string, which is the real line, and placing it in R2 in some way. So we see here that this path is actually describing a line which is passing through the point 3, 0 and in the direction minus 3, 2. So as we vary t, as we vary our parameter, that is going to give us a different position on our path, on the outputs of our path. So we want to think a bit more about what we mean by saying this function describes a line. What do we really mean here? Well, when we say that this function describes a line, we mean that the image of this function, so the outputs, so this is going to be the orange line on the right-hand side over here. This defines a curve inside R2. So it's important to remember the difference between the path, which is a function, which is something that takes in inputs and spits out outputs, and the image of this function, and that's going to define for us a curve. So the curve is a collection of points inside some vector space. The path is a function which is going to spit out outputs inside a vector space. So the trajectory of x is the way in which the curve is traced out as we let this parameter t increase. So let's have a look at a little animation to see how this all works out. So here I'm using Mathematica, which is a computer algebra software package that we will be using very soon and throughout the rest of the course. So all of this code that says here, this is what I require to plot the curve, which is this straight line inside R2. So if I want to think about the trajectory of the path, the function, then I have this following animation. So as t is increasing from minus infinity all the way up through 0 through positive real numbers, the trajectory is going to be the way in which the curve is traced out. Here's an animation. So these numbers here are t, different values of t, and so we see that as t is increasing, our curve, we're moving along this straight line. So this is the trajectory of this curve, of this path. The curve is the blue line. The trajectory of the path is the way in which we are tracing out the curve that we've got right here. Okay. So the same curve can in fact be parameterized by different paths, so by different functions, and with different trajectories. And in this way, we'll say that each path gives us a different parameterization of the curve. So, for example, we could reverse a trajectory. So if I look at the following path, so this is a different path because as a function, it's a completely different function. The component functions are different, so it's a different path, but it's going to define the same line as we had before. You'll see this is the line passing through the point minus 6, 6. It's parallel to the vector 3, minus 2. And this is in fact going to give us the same line as we had before. And here, the point that we had to define our line is actually obtained after 3 time steps. Also, we'll see that we get a different trajectory because we're kind of going along this line in a different direction. So we can see this in the following animation. Here's this animation for this path. So we see that as the time is increasing, for different values of t now, we're tracing out the curve, but our trajectory is a different trajectory. We're going in the opposite direction. We're going in the reverse direction in this case. Okay, so that's how you could reverse trajectories, and we'll talk more about how you could do this in class. And we could also be really elaborate and very much over the top with a parameterization of the same curve. So this scary looking path right here defines, in fact, the same curve. It defines the same line that we've been looking at. However, the trajectory is completely different. So we have a different path. It's a different path because the component functions are completely different. So this path is in fact different to this path. So I should have probably called this path Z or something. But now we see that what's happening is as we're tracing out our curve, we are tracing the curve, but our trajectory has this weird kind of go forward 2 steps, back 1 step kind of motion. However, all the points that we're hitting are exactly the same points as we've been hitting before, but now we're kind of double counting points. We're going back over some points that we may have already hit in our trajectory. This example is just supposed to highlight that the curve is the same, but the trajectory, the way in which this little red dot is moving around, is completely different. Okay, so now I want for you to stop the video and think about the following well-known parameterization of the unit circle. I want for you to think about how you could come up with 2 further parameterizations of the unit circle. Okay, so here is the given parameterization. This parameterization is going around the unit circle counterclockwise, starting at this point when t is equal to 0, and we're moving around in this direction. An example of a different parameterization is given by this path. This is, I've just swapped the sine and the cosine. And what's happening here is that, in fact, now we are starting from on the y-axis at time t equals 0, and now we're actually moving around clockwise. We also have this parameterization, this path. So parameterization of this curve. We have a different path. And now, in fact, if we look at this path, we're going to start all the way over here at the negative x-axis and then move around counterclockwise again. The interesting thing here is that if we look at our parameter domain, then this parameter domain is much smaller than these two parameter domains. And so if we think about this in terms of distance and speed, well, this parameterization is going to go round the circle once. So I'm going the same distance as these two parameterizations, but I'm doing it in less time. So we'd expect this to correspond to the fact that this parameterization should be moving around. As I let t increase, I'll be going around the curve. My trajectory will be faster, so we'll have a faster speed. And we'll discuss that more in a second. So, okay, before we get to speed, we need to talk about what velocity of a path means. So given a path x of t, we can define its velocity vector to be the following Newton quotient. So it's completely analogous with what we've defined for derivatives of functions in your first calculus classes. However, here now, all of our operations are subtraction of vectors and scaling of vectors. And so we talk about this limit, assuming this limit exists, just in the same way as we would usually, but now our operations are happening inside a vector space. So if this limit exists for all t, then we can talk about the velocity of our path. And in this case, we'll say that x is a differentiable path. So I should also note here that, in fact, this t should actually be a t0. So in fact, this velocity vector, whilst it looks scary because it has a limit, we can actually figure it out quite straightforwardly just by taking the derivatives of each of the component functions of our path. So in fact, the velocity vector is obtained by just differentiating each of the component functions of our path. So we also define the speed of our path to just be the magnitude of velocity, and we'll define the acceleration of the path to be the second derivative of the path, or the derivative of the velocity vector. So here's an example. So consider the parameterization of the unit circle. And again, let me just go back. So to interpret this velocity vector, so here if we look at our path x of t, traced out, giving this curve, the blue curve, and this quotient that we have right here, if we look at the difference, that's going to give us these position vectors. And so if this limit exists, then the geometric interpretation is that we're actually getting a vector that's going to be tangent to this curve and pointing in the direction that our trajectory is tracing out. Okay, so here is our example. So we're going to take the parameterization of the unit circle that we had before, and we compute, just by differentiating each component, its velocity to be this, and we can compute that its speed, so just the norm, the magnitude of this vector, is going to be equal to 1. So here, an interesting thing is that the path is given by this parameterization, and the velocity vector corresponds to these vectors. And what's true is, well, if you took the dot product of the path with its velocity vector, then it's a fact, and we can see straightforwardly that the path is in fact perpendicular to its velocity vector. So this is not something that happens all the time. This is a very particular and very special situation, but this makes sense if we think about a line being tangent to the circle, or a vector being tangent to the circle at this point. We'd expect that this should be at right angles to this line segment from the center to the point on the surface of the circle. We could also reparameterize the unit circle and give a different parameterization as follows. So here the velocity vector is nearly the same, but we've scaled it by 2 pi, and when we now compute the magnitude, we see here that the speed is going to be larger. And again, if we look back, we're going the same distance around the circle, but the different parameterizations have different lengths, different intervals of different lengths. And so we'd expect that should correspond to, if we go around in less time, our speed is going to be greater. And here indeed we see that our speed is greater than the speed when we go around over a longer interval. Okay, so now that we have the notion of a velocity vector, we can now talk about tangent lines of parameterized curves. So given a path, the tangent line to that path at a point on the curve, so remember the curve is the image of all points of the path, is the line through that point on the curve that's parallel to the velocity vector. We think of our curve as being this blue trace we've got here. Then we take a point on the curve, and the tangent line is going to be the line that's going to be parallel to the velocity. So if we compute the velocity vector, then we take this line that we've got here. So of course, this tangent line is only defined whenever the velocity vectors are non-zero. If the velocity vector is 0, then we have no direction vector with which we can define our tangent line. Okay, so let's finish off with an example. We're going to think of the circular helix. So the circular helix is a path, and you can check by noting that the component functions of the circular helix satisfy that x squared plus y squared, or x of t squared plus y of t squared, is equal to 1. So that means that this path must lie on a cylinder. So we already saw on Monday's class how to describe a cylinder in space. And so the curve, the circular helix, corresponds to this red curve that we've got over here. So the velocity vector is this vector here, and the tangent line to the path, to the curve, at the point x of 2 pi is given by this formula right here. So here, this is the point x of 2 pi, and this is now my velocity vector at x of 2 pi. So observe here that I've just replaced t by 2 pi in the definition of the velocity vector, and that now gives us this description of the tangent line. So here it's useful to remember is that the tangent line should use a different parameter than the parameter that you've used to define the circular helix, because these parameters are obviously corresponding to different geometric objects.